All right, so in this example, we're just going to put together what we know about critical points and inflection points to help us draw an accurate graph of a function, okay, using calculus. Now, I know you could probably graph this on a graphing calculator, or you could use any number of online tools to graph this. But what I want you to do is use calculus to justify your answers here. All right, so we're going to use calculus. We're going to use calculus, not a calculator or some online tool. So well, let's look at what the problem says. We want to determine the x and y intercepts. We're going to identify the critical points, determine the intervals for which the function is increasing or decreasing, and classify the critical points as maxima, minima, or neither. We're going to find all the intervals where the function is concave up or concave down and determine the inflection points, all this stuff. And then we're going to use that to help us graph the function. All right, so there's a graph down here and sort of a table where we can fill in our results. But let's just start by looking at this function. All right, now the y-intercept occurs when x is equal to 0, and the x-intercept occurs when y is equal to 0. So let's start there. That's easy enough. So if we want to know the y-intercept, we need to find f of 0. All right, so I'm just going to plug in 0 and see what that gives us. Well, if I plug in 0, it just becomes 0 e to the 0, which is just 0. Okay. And the x-intercept occurs when y is equal to 0. So I can just set x e to the minus x equal to 0. Now, there's two factors here. We have the factor of x and the factor of e to the minus x. So if x is equal to 0, that's one place. That's one x-intercept. And we know also that e to the minus x is never equal to 0, can never be equal to 0, right? Because e is a positive number, right? And we're raising it to some power. We can never raise a positive number to any power and get something less than 0 or even equal to 0. So that part is never equal to 0. So basically we found that the x-intercept and the y-intercept are the same thing. So let's put that in the little table down here. So our x-intercept is 0, 0, and our y-intercept is the same thing, 0, 0. All right. Well, that part's easy enough. All right, so that gives us the x and y-intercepts. Now we want to find what else? We want to find the critical points, right? We want to find critical points, which means we need to take the derivative of this thing. The derivative of this thing requires the product rule, right? Because we have two things multiplied by each other. We have x and e to the minus x. Okay, so we need to use the product rule. So the derivative of f of x is going to be, take the derivative of the first, we're going to call the first x, and the second e to the minus x. So the derivative of x is just 1, right? And times the second, and then plus the first, which is just x, times the derivative of the second. All right, so the derivative of e to the minus x is going to be e to the minus x times the derivative of minus x, which is basically minus 1. Okay, so let's rewrite this a little bit so it's a little bit neater. So we basically have e to the minus x, and then we can, when we take minus 1 times all this, I'm just going to turn that into subtraction. X e to the minus x. All right. Now to find the critical points, we have to set that equal to 0, right? And find where what x values make that 0. So to make that a little easier, I'm going to factor out this e to the minus x, right? Because I have two terms, e to the minus x minus x e to the minus x. So if I factor out an e to the minus x, then what I'm left with is 1 minus x. And I want to set that equal to 0. So I have two factors, right? We already said that e to the minus x can never be 0, right? So the only way that this derivative is going to be 0 is if 1 minus x is equal to 0, all right? And that occurs when x is equal to 1. So there's a critical point at x equals 1. Okay, that's our critical point. But we don't know whether it's a maxima or minima unless we test it, right? So we could take the second derivative and use the second derivative test, but that requires you using the product rule again. So I think it's probably easier just to test some points on either side of the critical point and determine whether it's changing from increasing to decreasing or decreasing to increasing. So let's just take some points on either side of 1, right? So let's look at the first derivative at 0. That's easy enough, right? E to the 0 times 1 minus 0 just is equal to 1. And that's greater than 0, right? So the function is increasing. The function itself is increasing to the left of 1. Now we can choose another point on the other side of the critical point. Let's choose 2. So e squared and then 1 minus 2. Now, okay, 1 minus 2 is a negative 1. So this essentially is a negative e to the minus 2, okay, which is basically negative 1 over e squared. All right. So remember, e to any power is going to be positive, but then it's the negative of that. So this is, let's see, let's make this into, this is less than 0. Okay. So that's telling us that the function is decreasing to the right of the critical point at 1. Okay. So the function is changing from increasing to decreasing, and so we have a local maximum. Local max at x equals 1. Okay. So I know I'm going to have to graph this, so I might want to put, I might want to draw my little number line, but maybe I'll wait. So now we know there's a local maximum at 1. Well, I guess we could have, I've got to take the second derivative. I think I said, well, let's not take the second derivative because it requires the product rule again. But if we want to analyze the concavity, we've got to take the second derivative either way. All right, so I'm just going to come over here. Let's take the second derivative of this thing. All right, well, I've got a couple of different forms of this equation. I've got the factored form, or I've got the original, or this one. So I think I'm going to take this form of the equation here, probably be easy enough, and take the derivative of that. All right. Either way, I have to take the product, or I have to use the product rule, but I'll just use that first form. So the derivative of e to the minus x, right, is I have to use the chain rule because I've got that minus x. So I have e to the minus x, that's the derivative of the outside function, and then the inside function is this minus x. So that's derivative of minus x is minus 1. So I'm just going to write this as negative e to the minus x. All right, and then I'm going to take the derivative of the second part, which is minus x e to the minus x. Okay, so all right, so the first is minus x and the second is e to the minus x. All right, so I'm going to take the derivative of the first, right, the minus x, so that gives me minus 1, times the second, e to the minus x, plus the first, which is a minus x, all right, so I'll put that in parentheses because it's plus a negative x, times the derivative of the second, which is e to the minus x, and then I have to use the chain rule. Right, so I got to multiply times negative 1. All right, it gets a little complicated because there's a lot of negatives going on there. You got to make sure you don't lose any of your signs. All right, so let's clean that up a little bit so we can see what we got. We got minus e to the minus x, and then this is also, this is negative 1 times that, but I could write it as minus e to the minus x. And then I've got negative x times negative 1, which just becomes positive x e to the minus x. All right, and I can combine these two terms. Minus e to the minus x is a minus 2 e to the minus x, and then plus x, e to the minus x. Whew. Okay, a lot to keep track of there. It's really easy to make a sign error. But let's see. Now I can also factor out that e to the minus x, because I know to find the inflection point and analyze the concavity, I've got to set this equal to 0, right, to find the inflection point. So it might be better if I have this in factored form. And I can factor out an e to the minus x. And what I'm left with is a negative 2 plus x. Or I could write it x minus 2. So if I set that equal to 0, you can see again the e to the minus x can never be 0. So this is only going to occur when minus 2 plus x is equal to 0. So I have a possible inflection point at x equals 2. At x equals 2. But I have to test it. I have to see if there's a change in concavity on either side of 2. All right, so let's evaluate the second derivative at some points on either side of 2. So let's look at f prime of 1. Okay, so that's to the left of 2, right? So if I put that into the second derivative, I'll use this final factored form. So that's e to the minus 1, and then minus 2 plus 1, right? So it really doesn't matter what e to the minus 1 is, but you can tell that negative 2 plus 1 is going to be negative, right? So I guess I could write it as minus e to the minus 1. That's a negative number. It's less than 0. So we know that it's concave down to the left of the inflection point. All right. So then we can also look at a point to the right of the inflection point. Let's look at 3. Okay, I plug in 3, I get e to the minus 3, and then negative 2 plus 3. I plug it into the equation for the second derivative. So I end up with, so negative 2 plus 3 obviously is 1. So this is a positive e to the minus 3. Okay. E to any power is always positive, so this is greater than 0. So that means it's concave up. Okay, it's concave up. So there is a change in concavity. So there is an inflection point at x equals 2. Okay, we've confirmed that there is an inflection point. Okay, so now we got to graph all this stuff. Okay, so so I know something about the, whether it's increasing or decreasing. I know something about the concavity. So let's kind of summarize this stuff. Actually, we could put some of the stuff in the table that we've been finding out. We found out that there's a critical point at x equals 1, right? We found out that it's increasing to the left of the critical point, right? So that would be on the interval negative infinity to 1, right? Not including 1 because at that point it's 0, right? So it's not really increasing or decreasing at 1. So I'm gonna make it an open interval. Okay. Now, in this particular chapter, they expect you to know interval notation, and so if you don't know interval notation, you might have to do a little bit of work to make sure you understand interval notation. So this is basically the same as minus infinity less than x less than 1. Okay, so just a different way of writing it using interval notation. Now we found out that it's decreasing to the right of 1, so on the interval from 1 to infinity, it's decreasing. Okay. There's a local maximum because we found that it's changing from increasing to decreasing. There's a local maximum at x equals 1, and that was our only critical point. So we don't have any other candidates for extrema, and so there is no local minimum. All right. And then we also found stuff out about the concavity. We found out there's an inflection point at x equals 2. And to the left of that, so from minus infinity to 2, the let's see. Yeah. Was it minus infinity to 2? Have to look here. To the left of it was concave down. Uh-oh, I got this backwards. All right. So it was concave down to the left of the inflection point. So let me fix that. This one should be minus infinity to 2. And then it was concave up to the right. So this should be 2 to infinity. All right. So, okay, let's use this to graph the function. All right, so let me just draw a little number line here to kind of get a picture of what it's going to look like if I just draw my arrows. All right, so we found that it's the critical point was at 1, the inflection point was at 2. Okay, so it's increasing to the left of 1. The function is decreasing to the right of 1. So it's also decreasing to the right of 2. Okay, and then it's concave down to the to the left of 2. Concave down. So here it's concave down and increasing, so it has this kind of curvature. Here it's concave down and decreasing, so it has this kind of curvature. And then on the other side of 2, it's concave up, right? But it's still decreasing, so it has this sort of curvature to it. All right. Now, the other thing we need is some points, so we can evaluate the points 1 and 2, because those are kind of some, that was where our critical point was and our inflection point was, so it might be nice to be able to graph those actual points. So I need the value of the function, f of 1, all right, I can just put in 1, right, and so our function was x e to the minus x, right, so it just becomes e to the minus 1, which is basically 1 over e if you want the exact value. But if we're going to graph it, it'd be nice to have some idea of of its value as a decimal. Okay, so it's approximately equal to 0.37. And f of 2 is going to be, again, the original function was x e to the x, so it's 2 e to the minus 2. So that's equal to 2 over e squared. And if I put that in my calculator to get a decimal approximation, it's 0.27. All right, there's a lot of information there. Let's try and graph it. All right, so 0.37. So it looks like this is about 0.25, 0.5. Okay, so 0.37. It's at 0.37. So I'll just say it's roughly there. Okay, that's our value of the function at 1. So I can just actually label that point 1, comma 1 over e if I want to label the exact point. And then at 2, we're at 0.27, so it's roughly about there. And I can label that if I want to. It's 2, comma 2 over e squared. Okay, that's the exact point. All right, and at 0, we also know this point 0, 0, right? Because that's our x and our y intercept. All right, so now we know it has to be concave up all the way concave down, I should say, concave down all the way from 0 to 2. Okay, so it's going to have this downward curvature all the way. See if I can make this look reasonable. It's concave down all the way to 2, all the way along this function. It's concave down. But it changes from increasing to decreasing at 1. Okay, so you can see here it's concave down and decreasing. And then on the other side of 2, to the right of 2, it becomes concave up. Okay, it's still decreasing though. So it's going to have some curvature that's more like this. All right, so there's kind of a sketch of what this graph looks like. Just kind of sketching it in. All right, so this is our local maximum. And this is our inflection point. Inflection point. All right, that was a lot of work. So anyway, that's all there is for this video. It got kind of long, almost 20 minutes here now. But this is very much like the discussion question. There's only one discussion question, and it's essentially the same thing where you're just using the derivatives, using calculus to help you sketch a graph. All right, So that's enough for today. I will see you in class.